Right, students, let us review Arenes class exercise 2. Right, so for question 1A and B, there is one directing group. Okay, so I'm just going to highlight this. So this is what we call amides, and this is ketones. So if I'm going to sketch out the structure, it will look something like this. So you have a phenyl ring and H, C double bond O, and a CH3. Okay, so let's also take note of the lone pairs of electrons on nitrogen. Okay, so if you're unsure of, you just go to the data booklets. Okay, so for the data booklet, you just look through the list for activating and deactivating groups. Okay, so now that I think you will find this familiar. So this is the amides. When it's drawn or written this way, the phenyl ring is directly bonded to nitrogen. Okay, so I think this is the only way that's being represented here. So if you look at the fourth last page of your data booklets, section 8, there will be a section on the orientating effect of groups in electrophilic aromatic substitution. Right, if you remember what I mentioned in the tutorials, I think I did categorically mention that if you are very familiar with what's going on, you do not need to reference this particular page, because sometimes referencing this page will cause you to have more confusion. Okay, so of course, in the beginning stage of learning, you might want to make reference to it at one point or another. Yeah, okay, so just take note that sometimes swapping the groups around or even protonating one of the group will cause the effect to change quite drastically. So for example, for NH2, it is 2,4 directing. In fact, it is 2,4,6 directing. Okay, so if you have phenolamine, you add aqueous bromine to it, the bromination will happen at the second, fourth, and the sixth position simultaneously. But if I simply just protonate the NH2 group, okay, it becomes a deactivating group by virtue of the fact that the nitrogen gains a positive charge, so it makes it inductively withdrawn. Okay, so going back to our class exercise. Okay, so over here, so it's an electron, on the whole, it's an electron donating group, or we call it activating group. So I'm going to expect the Br to be substituted in either the second, okay, or the fourth position. So I'm just going to draw this out again. Okay, so I'm going to expect two answers here. Okay, so I'm just going to draw in the fourth position, the Br. Okay, right. Okay, so maybe a little bit of explanation that might not be exactly relevant, at least for now, because it might be a little bit more impactful in the future, is that we have a lone pairs of electrons here. So let me explain a little bit why is it 2,4 directing. Okay, so CO is the net electron withdrawing groups. Okay, so delta minus delta plus. So electron density here will be withdrawn towards, okay, the oxygen. Okay, but at the same time, I have a phenyl ring here. So when I have a phenyl ring here, I'm just going to draw out the pi electron cloud, something like this. Okay, so if I draw the nitrogen in, the lone pair will be found at the p orbital because it can overlap partially into the phenyl ring and is parallel, and that makes the overlap good. Okay, so I'm just going to extend the bond out. Okay, so this is the CO, and then the CH3 here. Okay, so what's going to happen is that the lone pairs of electrons, right, will overlap partially with the CO, okay, and it will be withdrawn towards the O. At the same time, it will also overlap partially with the pi electron clouds of the benzene ring. Yeah, so it's a bit of a tug of war. Which side wins? Okay, so of course oxygen is more electronegative than carbon, so electron density will largely be withdrawn towards oxygen rather than carbon. Okay, so I'm going to expect a greater percentage of the electron densities on nitrogen to be withdrawn towards oxygen rather than the phenyl ring, but the net effect is still electron donating. So that's why if you have an amide with the phenyl ring bonded to the nitrogen, the directing effect is 2 and 4. What's going to happen if the phenyl ring is bonded to carbon instead? So if it's the other way around, okay, I'm just going to use the space here. So if it's the other way around, for CO and CH3, for example, I have a phenyl ring, right? So by and large, we're going to expect this to have the same answer as part B. This is by and large an electron withdrawing group. So electron density will be withdrawn towards the oxygen. Okay, so withdrawn from the phenyl ring to the oxygen effects. So when that's going to happen, as what we might have gone through in the guided inquiry, you know that the incoming electrophile would prefer to be substituted at the third position rather than the second and the fourth position. The reason being, if it's substituted at the third position, it's going to avoid having a resonance structure with a positive charge directly bonded to the substituent. So it will lead to less destabilization. Okay, so if I'm going to swap my amides around, I'm going to end up with substitution at the third position rather than the second or the fourth position. So that also allows me to draw the answer for part B, because for part B you have an electron withdrawing acetophenone group. Okay, so a CH3 here, CO is electron withdrawing. I'm going to draw in the phenyl ring. Okay, and then the Br will be here. Okay, at the third position. Okay, so I think I've answered part B by sort of discussing what happens when I flip my amide around, allowing the phenyl ring to be bonded to carbon instead of nitrogen. Then some of you might ask, what about the lone pair here? Yeah, so the lone pairs here will have no effect on the phenyl ring because it will be withdrawn towards the oxygen, so it will not be able to interact much with the phenyl ring. Okay, yep. Then what about part C? Okay, so part C we need to analyze a little bit, but usually for assessment purposes it will not be too difficult. Okay, so if you need to reference to the data booklet, please go ahead. If not, I will just use arrow of different color to illustrate to you. Okay, an O-methyl group will direct electrophile to the second, okay, fourth, okay, or sixth position relative to the OCH3. Okay, but the fourth position is not possible because there is already a substituent NO2, so I'm going to erase it. Okay, then next I'm going to use red. Cl will direct the incoming electrophile to the second position relative to it. Okay, the fourth position relative to it, as well as the sixth position. I'm not going to draw it in because it already contains the NO2. Then next, NO2 is 3 directing, so it will direct electrophile to the third position relative to it, as well as the other position, which is the fifth position. So when you consider all this, 3 arrows all at position, I'm going to highlight in orange here and here. So therefore my answer will be, I'm going to draw the answer out. Okay, so it will be OCH3, draw it out. Okay, phenyl ring, Cl and NO2. Okay, and then a Cl here. Okay, and then plus OCH3, phenyl ring, NO2, Cl and Cl. Okay, yep, but this answer is less likely. Okay, so this is less likely for a very simple reason, because I have 2 bulky groups here, so I'm just going to erase it first. Okay, I'm just going to circle the bulky OCH3Cl here. So it will make the incoming electrophile to the second position relatively difficult, because when the electrophile approaches that position, it will experience steric repulsion. Okay, so the activation barrier is likely to be higher as compared to when it approaches here. Yeah, so normally if you are only required to draw one answer, I will draw this answer rather than this. But of course, theoretically, it's not wrong to draw this. Yeah, but if there's only one answer I need to draw, then I will be drawing the one I've circled and put as a star. Alright, okay. Then next, dilute HNO3. So dilute HNO3 tells us one thing. even in the presence of OH, NO2 will not be directed to too many positions. Okay, and at the same time, because OH is a very strongly activating group, I'm going to expect the condition to be mild. Yeah, so in this case, instead of using corn sulfuric acid, corn nitric acid, I'm just using dilute nitric acid. Okay, yep. So what's going to happen is, again, same logic. In terms of directing effect, OH allows NO2 to be directed second position relative to OH, fourth position relative to OH, as well as the sixth position, but it's already occupied by Cl. Okay, and then at the same time, I'm going to use the purple pen. Okay, so it will be directed, for Cl here, it will be directed second position relative to it, and then fourth position relative to it. Sixth position is already occupied by OH, so I will not draw it there. Okay, so what have we noticed? We noticed that it might be a competition between the green and the purple arrow, but in reality, do we draw any answers? Okay, so of course, the answer is no. Yeah, so when you have two competing groups, one is a strongly activating group, the other one is a weakly deactivating group or a deactivating group, the directing effect will always follow the activating group. Okay, so therefore I'm going to draw only one answer. Okay, so I'm going to draw Cl, okay, and then OH, NO2, okay, as well as Cl, OH, NO2. Okay, so I'm just going to draw these two answers. Which is the more likely product? This is likely to be the more likely product, but because the incoming electrophile will only be approaching the second position with only one OH next to it, so I think the activation barrier is not going to be a lot higher as compared to when it approaches here. Okay, so I think drawing two answers still make a little bit more sense, but of course if I were forced to only draw one answer, then you should be drawing this. Okay, question 2. Question 2, we have suggest suitable reagents and conditions for the synthesis of compounds. Okay, given starting material. Okay, so you're supposed to draw the structures of intermediates and products in the boxes provided. So we start off with a benzene ring, and then we end up with two bromonitrobenzene. Okay, so you know that you're going to introduce two groups in, Br and NO2. Okay, so let us just go through a thought experiment. Okay, because I mean, there's only two steps. Okay, one intermediate. So your intermediate will either be bromobenzene or nitrobenzene. Yeah, so it's either you brominate first or you nitrate first. Okay, so the question to ask ourselves is, what is the relationship between Br and NO2? So if you look at the products, the relationship is a 1-2 relationship. So because they are in a 1-2 relationship, you would expect that whatever groups you introduce first must be able to direct the next electrophile in the second step into the second position. Yeah, so and you know the nature of Br and NO2. Br is weakly donating, which will direct the incoming electrophile to the second or the fourth position. NO2 is strongly deactivating, so it's going to direct the incoming electrophile to the third position relative to itself. So therefore, based on this particular logic, if you're going to introduce Br first, the chance of you having NO2 in a position next to it is significantly higher as compared to when you introduce NO2 first, because when you introduce NO2 first, the Br will likely be directed to the third position. So because of that, I'm definitely not going to form nitrobenzene first. I'm going to form bromobenzene first. So I hope you get this particular thought process. Okay, so if you're not able to get this particular thought process, you can draw both bromobenzene and nitrobenzene, and then you try to draw the product after that. Then you decide for yourself which is likely to give you a significant yield of 2-bromo-nitrobenzene. Okay, yeah, so this is of course not a very time-saving way to answer the question, because if you heard me, I asked you to draw two intermediate first. Yeah, but when you are more experienced, you're not going to do that. Okay, so I'm just going to draw out the answer first. Okay, so the answer I'm going to draw will be bromobenzene, Br. Okay, and then of course to form bromobenzene, the condition will be similar, Br2 liquids. Okay, so Al Br3, and then warm it. Okay, and then in order to direct the electrophile to the second position, I'm going to use harsh condition, con HNO3, con H2SO4, and then heat at around 50 degrees Celsius. Okay, or maybe I can actually just put heat. I think heat will be sufficient. Okay, why do I need to heat? Because Br is withdrawing, so it will make the reaction more reluctant to take place. So I will need to increase the temperature further. But exact condition not important here. Okay, we look at part B. Okay, part B has more steps. Okay, so I'm just going to highlight the important groups. Okay, so we have benzoic, or rather we have carboxylic acid and NO2 in a 1,4 relationship. Okay, so again a thought experiment. Am I going to introduce carboxylic acid? No, there is no such thing as a carboxylic acid electrophile within what you have learned in your curriculum. Okay, so what is the closest to a carboxylic acid? If you remember the parts of your curriculum for arenes where you undergo side chain oxidation. Yeah, so for side chain oxidation, you're going to expect to produce a side chain, introduce a side chain first, and then after that you allow side chain oxidation to take place to convert it to a carboxylic acid. Okay, so with all this in mind, you might want to first perform an alkylation or a methylation to introduce methyl group in. Okay, then you'll be thinking, but shouldn't I nitrate first? Why don't I nitrate first? Okay, so that become something that again you can go through the thought experiment, which earlier on I asked you to go through. If you do a nitration first, your group will be directed to the third position, but your carboxylic acid and your NO2 is a 1,4 relationship. So definitely you can't nitrate first. So you can only nitrate later. Okay, so with this in mind, let us try to alkylate first or methylate first. Okay, so again, same thing. CH3Cl, AlCl3. I warm it. Okay, so I'm going to introduce the methyl groups and to produce methyl benzene. Okay, so next thing I'm going to do is do I need to perform side chain oxidation first? So again, if you perform side chain oxidation first, so suppose you perform side chain oxidation first, your NO2 in this step will be introduced into the third position, but the relationship between carboxylic acid and NO2 is 1,4, so therefore I cannot perform side chain oxidation first. I will need to perform electrophilic substitution of NO2 first. So again, this will be the same thing, con sulfuric acids, con nitric acids, maintained at 30 degrees Celsius. Okay, and then the final step will be to perform side chain oxidation by using KMnO4, H2SO4 heat. Yeah, so I hope with this little explanation, it becomes a little bit clearer what you need to do to achieve the product. Do not be too stressed at this stage for a very simple reason, because I mean, a lot of things are not very clear to you, and I mean, leading up to promos, you're only being tested 2 topics. So Arenes is actually the third major organic topics other than intro, organic chem, and isomerism. So do spend a bit of time to think through how to link concepts up. It might be easier. Okay, right, so next, part C. Okay, so part C is interesting question, because part C you only have 2 steps, and what's going to happen is that you go from 10 carbon to 8 carbon. So there are 8 carbons here. So if I'm going to do a carbon count here, so that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, then over here 1, 2, 3, 4, 5, 6. Okay, so 7 is likely to remain. And then what's going to happen to this? How come suddenly there's a carbon here? So this carbon here is likely to come from one of the carbon in the side chain, 8, 9, or 10. Okay, then as per all problem solving strategy, I'm just going to introduce this particular strategy that will help you a lot in JC2. Okay, I'm going to write out the molecular formula of the starting material. So that will be 10 carbon. H's will be 5, 6, 7, 8, 9, 10, 11, 12, 13, H13Cl. I'm just going to subtract away my intermediates. Okay, I'm going to end up with HCl. So therefore, for step 1, HCl is lost. And how can HCl be lost to form this particular intermediate product? And what can I do to the intermediate product in order to produce a dicarboxylic acid? Yeah, so based on our guided inquiry worksheet and some of the things you have learned regarding side chain oxidation, it is likely that C10H12, the intermediate product, has 2 side chains. Yeah, so if I'm thinking along the line that maybe the side chain look something like this, okay, some of you might draw it like that. This will be wrong. Okay, why is it wrong? Because there's only 8 carbon. Yeah, I need to draw something with 10 carbon. Yeah, so how can I transform my starting material into something with 10 carbon and at the same time fulfill the criteria, so much so that when side chain oxidation occurs, okay, only 2 of it remains as carboxylic acid. Yeah, so most likely the thought process is there's a Cl here, not for fun, but maybe if you reference it back here, if I want to introduce an alkyl group into a benzene ring, I will perform alkylation. So the Cl here might be a clue that I need to perform an alkylation. Okay, and then I need to warm it. Okay, so when this happens, I'm going to get a benzene ring, okay, with a side chain like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is likely to take place. Okay, then some of you might be wondering, how can this take place? The carbon 10 seems to be very far apart. It's not that far apart if I choose to draw it like this. Okay, so I hope you can agree with me that it's not that far apart if I draw it this way. So this delta plus, delta minus. If you remember your electrophilic substitution mechanism, okay, this will be a nucleophilic CCl, so it will attack the electron deficient aluminium Lewis acidic group. Okay, then in the process you will generate an electrophile, okay, like this. Of course, this electrophile is not stable. It's not particularly stable because it's a primary electrophile. Yeah, but what I can say is simply, given whatever knowledge you have for now, this will be the best examples, or rather, I should just write it as AlCl4 minus. This will be the best way you can draw the mechanism. Okay, and then of course, the electron density of a phenol ring will attack the electron deficient carbon, and then in the process, I will generate this particular intermediate. Okay, if I were to draw a semi-crescent, I can draw that. It's H here. Okay, then the H will be lost. Of course, I will need AlCl4 minus. Okay, and then we'll grab the H. Okay, and then eventually HCl will be lost. AlCl3 will be regenerated. Okay, and then I will get a product that looks like this, plus AlCl3. Okay, yep. Then after that, I'll perform side chain oxidation. Then side chain oxidation condition is the same as the one in 1B. Okay, some of the students who are a little bit more advanced, they might ask me, this is not stable, so can it very quickly equilibrate to give you to perform what we call a hydride shift to produce a more stable carbocation ion? So of course the answer is yes, it can happen. So hydride shift simply looks something like this. The H will just shift here to produce a more stable secondary carbocation ion, and then they will attack. So eventually you'll end up this as the intermediate. Yeah. Whether you draw this or this, it doesn't matter, because I will get the same product eventually if I perform side chain oxidation. Okay, yep, so that will be the end of the review for class exercise 2. So the next time we're going to discuss will be next year for acid-base equilibrium. Thank you very much.